Good evening, guys, and welcome to it. This is our very own favorite show where you learn more and learn extra on a lovely Tuesday where we do physical sciences. My name is Abram, and welcome, guys. We're doing the show with Tiniko. TK, how are you?
I'm good. Yourself, Abram?
All good. I'm superb.
Yes, nipukile but nitsamsekile ni ready science here.
Yeah, Yipa.
Aiba.
Yipa off.
Yes.
That's why in the spirit of Africa Day. I hope you enjoyed Africa Day yesterday.
Well, it was a great day. Actually, going to work in the morning and, local radio stations playing African songs, know. It's like I moved out of South Africa into other African states for a while. And when we got to work, we also had this arrangement where, we had some function, Africa Day. How it felt, to be an African. So patriotic. I belong to Africa.
Of course, and I think one thing I like about being an African is food, We've got various kinds of food, nice food, good food, trust me.
Good food. And I had masonja, masonja.
Wow, nice
yes,
one,
I
nice
had
one.
that. I had
right,
that.
let's talk about food for the thought now. What are we doing today?
Well, today, Abram, we're looking at acids and bases, and matriculants would know that this is a section of work that comes from the knowledge area that talks to chemical change. So we're talking about chemicals, we're talking about how substances interact with each other. Obviously, when substances react with each other, Abram, we're expecting products to be formed and all those kind of things. But specifically today, we're talking acids and bases. So we'll be looking at how they interact with each other. What are these things in the first place and how they interact with each other chemically?
All right, I'm looking forward to it. It's going to be a great show, I must say.
Sure.
Well, for you to enjoy it with us, Matrix, you need to get the notes, and the notes that we have for you are also available from this workbook. It's only 139 rands. All you need to do is to send an email to sales@mindset.co.za. We'll tell you more about it. It's so important, guys, that you have it because it has got solutions as well. But otherwise, you can interact with me via Facebook, which is facebook.com/learnextra, or follow us on Twitter @learnextra. Trust me, during this time, I know some of you are panicking and exams are around the corner, but we're here to help you. So don't be left alone. Gear up with us because we are here to help you guys. If you're having any questions or comments about the show, send them through to me and I'll take them. Thank you.
Yes, thanks, Abram. And let's kickstart our lesson. And like I said, we need to know what these things are. Like when we talk of acids and bases, there are two main theories that you need to be aware about. We've got the Arrhenius theory of acids and bases. We've got the Bronsted-Lowry theory of acids and bases. And let's just have a look at what do they say about those substances. Starting with Arrhenius, you would see Arrhenius talks of an acid or defines an acid as a substance that releases hydrogen ions when in solution, in an aqueous solution. In other words, a solution where the solvent is water. Okay. And on the other hand, when he looks at a base, he says that a base is a substance that releases hydroxide ions, the OH minus ions, when it is in solution, in aqueous solution. So that is the first theory that we are to look at. Now, apart from the Arrhenius theory, the next theory that you need to be clear about when we look at acids and bases is the Lowry-Bronsted theory. And let's see what these two guys think or looked at acids and bases and tried to define them. Now, these guys came in because they looked at the Arrhenius theory and thought, look, it is limited in some way because it talks about an acid only if it is dissolved in water when it is in that solution, or a base in the same way. But can we tell about what an acid is or what a base is in terms of how the two would act with each other, how they will interact chemically? And yes, they came up with something, a theory that says, if you look at an acid in terms of how it reacts with another substance, if a substance in a chemical reaction donates a proton, that substance will be an acid. So they called that an acid. An acid is a proton donor. And on the other side, they looked at how bases would react in a chemical reaction, and they say any substance that would receive a proton in a chemical reaction will be called a base or will be a base. So for that matter, they would say A base is a substance that receives protons, or in summary, it is a substance that is a proton acceptor. It receives protons. Okay, now you would see that if you look at the Lowry-Bronsted theory, it talks to transfer of protons. One substance loses protons, another receives them. So there is a transfer of protons when that chemical reaction takes place. So because it's protons that are being transferred, we call those type of chemical reactions protolytic reactions because they involve the transfer of protons. Now, in this process of transferring protons, we see that some of these substances that will transfer protons, that will donate protons, obviously those are acids. Some of them would be able to only donate one proton. And if they donate one proton, we will call them monoprotic acids. You see, they can only give away one proton. So mono means once, so monoprotic acids. If they are able to give out more than one, we will call them polyprotic acids. Poly meaning many. Okay, so we will call them polyprotic acids. Now you will agree with me that when the substance is giving away these protons, many of them, some would be able to give away 2 or donate 2, some may donate 3, 4, whatsoever. But we'll stop at 3. Okay, so if we have a substance that donates 1, we say it's a monoprotic acid. If it can donate 2, we will call it a diprotic acid. For example, you may look at sulfuric acid. By its nature, if you look at that, if you look at that chemical formula, it's H2SO4, so it can donate 2 protons, okay? And therefore, it is a diprotic acid. If it can donate 3 protons, we will call it a triprotic acid. And example of that would be an acid like phosphoric acid, H3PO4, okay? That one can donate 3 protons, and therefore it is, if you like, what we call a triprotic acid. Now, in a chemical reaction, it does happen sometimes where we find that one substance is able to give away protons in one set of circumstances, in one particular reaction. But the same substance, in another set of circumstances, in another reaction, we find this substance receiving protons. So it can donate in one situation and it can receive on another. Remember that if you give away a proton, you are an acid. If you receive a proton, you are a base. So this substance, which is able to do both, it is some kind of a special substance. And we will call those type of substances ampholytes. This is a substance that can act as both an acid and as a base. Okay, an ampholyte, depending on what the other reactant is in that chemical reaction. Now, hydrolysis. Not going to talk much about this one because you're going to have a whole lot of it next week. But let me just summarize a little few things about it. Hydrolysis is the reaction between water and the ions in a salt solution. So hydrolysis would always lead to the development of either an acidic or a basic solution, depending on what the reaction is about. But it's about salts in solution, in aqueous solution, reacting and making that solution either basic or acidic, all right? Now, these solutions that we're talking about, we prepare them. If you prepare a solution and you know exactly what the concentration is, and we know that that concentration is going to remain constant, in other words, the same for a certain period of time, we call that type of solution a standard solution. So a standard solution is something that you need to prepare yourself so that you know what its concentration is about. Okay, now quickly, this is, if you like, going back as far back as grade 6, 7, okay, work, all right, where you need to remind yourself that when an acid reacts with a metal, you will always produce a salt and a hydrogen gas. When you have an acid reacting with a metal oxide, again, it shall be a salt and water, okay, as products there. And the same thing will be when you have got an acid reacting with a base. You will always produce salt and water if you have that type of reaction. And if you have an acid reacting with a metal hydroxide, calcium hydroxide, for example, salt and water will be produced. Acid, metal carbonates, you produce salt, water, and carbon dioxide. When you have an acid reacting with metal hydroxide, hydrogen carbonate, okay, you will produce salt, water, and carbon dioxide. So that is, in general, things that you need to know. Just general things about acids and bases, all right? Okay, now, quickly, coming to this. When we talk of the transfer of protons, transferring and receiving of protons, when an acid donates a proton during a chemical reaction, it will form what we call a conjugate base. In the same way, when a base accepts a proton in that reaction, it will form what we call a conjugate acid. Okay. In an acid-base reaction, the acid and the conjugate base it forms, as well as the base and the conjugate acid that is formed, all these, we call them, they are known as conjugate acid-base pairs. And you would see, I'll look at some example that would help you understand that concept later on. Strength of acids and bases. Now look at this. For them to understand how strong an acid is or how strong a base is, they had to go back to the first theory of acids and bases, the Arrhenius theory. A strong acid is an acid which ionizes almost completely in water. Okay, so contrary to that, a weak acid will be one that ionizes only slightly in water. Okay, and if it's a strong acid and it ionizes almost completely in water, it would mean that we have got a very high percentage, okay, of ionization of that substance. So many ions of that substance are formed in that solution. And therefore, that means the concentration of the hydrogen ion or the hydronium ion in that solution is very high. Okay, so a strong acid would always have a weak conjugate base. All right, I have already explained what a weak acid would be, obviously, so that's enough. Let's move on to the strong base. Strong base will dissociate almost completely in water, whereas a weak base will dissociate only slightly. It will dissociate only slightly in water. All right, and a strong base will have a weak conjugate acid. And likewise, a weak base will have a strong conjugate acid. Okay, all right. Now, ionization, autoionization, quick one here. Autoionization of water. Auto means self. So water is ionizing on its own. Water is able to do that. It ionizes to give us the hydronium ion and the hydroxide ion. And from here, we come up with what we call the equilibrium constant of water. It's a special constant. We call it Kw, okay? And it's a special constant because you would know that when you work at Kc, you've concentration of products divided by concentration of reactants. And in that way, you would see that the concentration of water is constant, and if it multiplies the Kc, it gives you this special one, Kw. Now, Kw is the ionic product of water, which is this. It's equal to that. If we have pure water, the concentration of H3O plus equals the concentration of OH minus, which will be equal to 1 by 10 to the power minus 14 mole per cubic decimeter. Okay, so that is what we would have there. Let me stop at that point and hand it over to Abram, and let's see how we move further after the break.
Thank you so much, TK. And a big shout out to all the guys that are watching. Shafi Solomon's, his gift in Chabileng, and everybody else, such as Tintswalo Paloy, enjoying the show, Khotatso, Lebeko. Thank you guys for tuning in, and Enoch with your friend Martin. Thank you guys for tuning in. Send through your comments and your questions, and we'll take them. Remember, it's facebook.com/LearnExtra. During this break, you'll be looking at a competition that we have for you. I'll tell you more about it. Welcome back, Matrix. Now, entering for the South Pointer competition is very easy. All you need to do is to fill in the entry form that I have for you on our Facebook page, and that's it, guys. But in case you don't see it, go to our website, which is learn.mindset.co.za. I've got a question from one of you from Nzulu Ngapai, saying, enjoying the show, but Abraham, please help me. How could I get that workbook? Well, guys, it's simple getting this workbook. All you need to do, you must put in an order, and you can get more information about ordering by simply sending an email to sales@mindset.co.za, or else I can just inbox you that email address, ask me on Facebook, and I'll tell you more about it. TK?
Yes.
I have a question for you.
You do, yes, let's hear.
Tabiso Madlanzi says, how do I identify that HCl is acid or base?
Oh, okay. No, well, that should be an easy one. Now, as we have explained, according to Lowry-Bronsted theory, if you check how HCl is reacting and you see that it is actually donating a proton, you will say it is an acid. Okay? Even when you go through Arrhenius theory, if you dissolve HCl in water, okay, you would see that it produces the H plus ions, hydrogen ions. That classifies it as an acid. And another thing that we're going to tell, you can actually test it, which is something that I'm going to talk about now, making use of the pH. If a pH is less than 7, it tells you that substance is an acid. If the pH is greater than 7, it tells you that that substance is a base. If the pH is 7, it tells you that that substance is neutral. Usually water, when you test it, or using a pH meter, it will tell you it's pH of 7. That tells you water is neutral. It's neither a base nor an acid. Okay, so I believe that Tabiso has gotten some answer to his question. Can I move on, Abram? I think
yes,
we can just quickly move on here. Quickly, the pH thing. I have explained what the pH is going to be for acidic solution. What makes it to be less than 7 is the fact that your concentration of the hydronium ion is greater than the OH minus ion. And in a neutral solution, your concentration of the hydronium ions or the hydrogen ions, H pluses, equals your hydroxide ions. And the pH will be 7 in that case. In an alkaline solution, what is an alkaline solution? This is a basic solution. It's a base. So here you would find the hydronium ions concentration being less compared to the hydroxide solutions, concentration, and therefore that makes the pH to be less than 7. Okay, now, how do we find this pH? pH is calculated by using the formula minus log the concentration of H pluses, okay? And what is this pH? pH of a solution is an indication of how acidic or alkaline a solution is. That is the degree of alkalinity or base or acidity of a substance, okay? Now, coming back to this, I want to take this one down here. You see we have got pH equals minus log the concentration of H3O plus ions. On the other hand, you can find also the pOH of a solution. That will be minus log the concentration of the OH minus ions. Okay, why am I doing it like this? Because the pH from the KW, pH plus the POH should give me 14 all the time. This is a useful formula. It's a useful tool that some books and sometimes you don't always get it. Okay, so please know this one and use it. I want us to move quicker now and move on to talk about some questions and see how we answer them. So we do some practice with you. All right. Let's look at this one here. Question 1. In an acid-base reaction, 500 cubic centimeters of solution of sodium hydroxide is completely neutralized by 680 cubic centimeters of solution of sulfuric acid. The equation for the reaction is as follows. So we have the equation there, where we've got an acid reacting with a base. We produce a salt and water. This is salt, sodium sulfate, and water. Okay, so that is your general equation now. Acid plus a base. All right? Now, the pH of the base solution before any acid is added is 13.8 at 25 degrees Celsius. Show by calculation that the concentration of the sodium hydroxide solution will be 0.631 mole per cubic decimeter. So you just show by calculation. Obviously, you will need to use the pH calculation here. So pH is equal to minus log. This is equal to minus log the concentration of hydronium ions or hydrogen ions, just simply H plus ions. Now, what was the pH of the solution before any acid was added? It was 13.80. All right. So you can say that this is 13.80 should be equal to minus log the concentration of what? Of 830 plus. Okay. Therefore, what will be this concentration here? The concentration of the H3O plus would be equal to what? It will be equal to 10 to the power minus 13.8. Okay? And that should work out to be. Now, from here we can find that concentration of the H3O plus ions. But the question wants us to find the concentration of the sodium hydroxide. We will see how we get there. So now, quickly, you make use of your calculator for this one. So you would say that I'm looking for 10 to the power minus 13.8. 13.80 is the same as 13.8. And that gives you 1.585. Okay, so the concentration of H3O plus is equal to 1.585, equal to 1.5. It's equal to 1.585. Must actually take out that as well. So 1.585 by 10 to the power minus 14 mole per cubic decimeter. Remember, you are calculating for concentration, so the unit of measurement there is mole per cubic decimeter. All right, don't know why this pen is letting me down today, so that should be a 3. Okay, so once you get that, you should be able to get the concentration of sodium hydroxide, because actually the concentration of sodium hydroxide is equal to the concentration of the OH minus in this solution, which should be equal to that should be equal to, remember, the 1 by 10 to the power minus 14, which is when they are together, all right? Then minus what? Minus the concentration of, let me just work it out properly here. Okay, maybe let me start here so that you see what is happening here. The concentration of OH minus times the concentration of H3O plus, these should give us 1 by 10 to the power minus 14. Okay, so we know the concentration of the the H3O minus, H3O plus ions. So the OH minus concentration should then be equal to 1 by 10 to the power minus 14 divided by what? By 1, that's the concentration of the H3O plus, this one here. We need to divide by that one there. So we would say divided by, that's what we found out here, 1.585 by 10 to the power minus 14. And what is that? We can then find the answer to that to be what? Let's get the calculator. All right, so we have clear that and we go there. We say 1 by 10 to the power minus 14 divided by 1.585. I need to take that out because I've already used the fraction, so let me come down here. 1.585 by 10 to the power minus 14. Okay, and what do we get? You're getting 0.631. So the concentration of the OH minus is equal to 0.631 mole per cubic decimeter. Okay, you can use that. But one may ask, and allow me to use this space here, down here, before that question. One may ask, is that the only way to answer that question? No, it is not the only way. Remember, I wrote earlier on that POH plus pH should give us 14. Now, if I'm given pH, I can find POH. So POH would be equal to POH would be equal to 14 minus pH. Now, if you remember what our pH was, you would put it in there. It's given to us. It's 13.80. So that will be 14 minus pH, which is 13.80. You work that out, it gives you a POH of 0.2. Now, pH or POH has got no unit, so I would leave it like that. Now, how do I then calculate the concentration of OH minus? Concentration of OH minus is equal to minus log the concentration, it's equal to, let me write down the formula in full here so you see where it comes from. Let's write POH. POH equals minus log the concentration of OH minus. Now I have the POH, which is 0.2, equals minus log the concentration of OH minus. Therefore, from here, concentration of OH minus should be equal to 10 to the power minus 0.2. That is your mathematics now. And this will work out directly to give you your 0.631 mole per cubic decimeters. Okay? Mole per cubic decimeters. So that's another way of dealing with it. But I still have to answer 1.2 on this one, so I'll need space here. I'll erase. I think you see what I am doing here, so you would be able to follow it up, okay? So let me create some space here so that I am able to answer the other question. All right. Good. It says, what is the difference between a strong base and a concentrated base? Beautiful question. Now, a strong base, you would know, according to Lowry Bronsted, a strong base will be one, according to Arrhenius theory, a strong base will be one that ionizes almost completely in water or in solution, in aqueous solution. Strong base, okay, ionizes almost completely in aqueous solution. Then that is therefore a strong base. Then the question is, what is a strong, what will be a concentrated base? A concentrated base, it's a substance that has got more ions per unit volume. So it has got more ions per unit volume in a solution. More ions per unit volume in a solution. That is a concentrated base. Concentrated base has got more ions per unit volume in a solution. That you need to get. It can be a very weak base, but being concentrated base. It's a weak base because it doesn't ionize almost completely. It only ionizes slightly in water. But it's a strong, it's a concentrated base because it contains more ions per unit volume. Okay? Good. Now calculate the mass of salt. The mass of salt used to prepare the base solution. And the base solution here is that of sodium hydroxide. Okay? From this formula here, concentration equals number of moles over volume. Okay? Number of moles over volume. I can write it in this way so that it can help me to get to the mass quicker, where I say concentration is equal to the mole, the mass given, divided by the molar mass of the substance times the volume in which the solution is prepared. And in this way, I will be able to say, okay, molar mass of sodium hydroxide. I need to work out this one. I think that will be, for sodium should be 23 plus 16 for hydrogen plus 1, and gives me 40. Yes, 40 grams per mole for sodium hydroxide. So if I want to know the mass, I can actually begin to substitute into this. The concentration I have calculated, we found it to be 0.631. So I'm beginning to substitute now. 0.631 should be equal to the mass that I'm looking for. The molar mass is 40 times the volume. The volume was what? The solution was in 500 cubic centimeters. 500 cubic centimeters in cubic decimeters is 0.5. Okay, so I'll multiply that by 0.5 and I'll definitely get what the mass is there. All right, let me hand over to Abraham. I don't want to kill his time before he kills me, but I think at that point you can actually calculate and get to the answer.
All right, thanks. Thanks, TK. I've got so many comments and questions for you after this break, but I must tell you guys that we're giving away our second Chevy Spark. All you need to do is to enter the Beer Bright Spark competition. It is closing on the 3rd of July, and the winner will be announced live on Len Extra Live on the 21st of July. So enter right now. We'll see you after this break. Welcome back, guys. Now, this is your segment where we take your comments and your questions. And firstly, a big shout out to, sorry, I forgot your birthday, to Ria Lucia. Happy birthday to you. And I know you're watching the show and enjoying it. This is the best birthday present ever, enjoying the show with us. TK, I have a couple of questions for you.
Yes. Let's hear them.
I must say this firstly, to Lebohang Morake, he's always on time, but today he's late, so he missed your explanation on the POH. I hope he got it now.
Yes.
The last bit of
it was here. The POH, Lebohang POH plus pH equals 14, and that is from the KW of water, where concentration of H3O plus times concentration of OH minus equals 1 by 10 to the power minus 14. That to the power minus 14, and the POH and pH, that's where it comes from.
Okay, a lot of the guys were asking the same question. Jomo Joannis, our regular, saying, hello, my question is on 1.1, where does the 10 come from? It's the same question that was asked also by Mabushadi.
Oh, well, maybe they are representing thousands that are out there. Now, let me explain where the 10 comes from. If we say pH is equal to minus log the concentration of H3O plus ions, the way it is written, this is log to the base 10. That is where the 10 comes from. So it's log to base 10. So that's why, because this is your base, and when we changed and worked out the concentration of H3O plus here, we said because there is a base 10 there, all right, then when we do away with the log, we're writing this as an exponent now. The base is 10, and the pH is that one, okay? So it's the base 10 to that pH, to that power, all right? So that's where the 10 comes from. You must, when you see that log, you must, I know it's not written all the time, but there's an invisible 10, log to base 10 of whatever, all right?
Okay, Shafi Solomon says, can you please elaborate more on the ionic product of water KW?
All right. Let me try a quick one on that. I'll try it in this way. From here, from the auto-ionization of water, H2O, auto-ionizing, so self-ionization, to give us H3O plus, H3O plus OH minus from there, okay? From this, we know that if I were to find the Kc, all right? So I can say this is 2H2O, this side, okay? If I want to write like that. Kc would be given by concentration of H3O plus times the concentration, so concentration of products times the concentration of OH minus. You divide that by the concentration of H2O to the power 2. Now, people want to kill me. They are throwing stones already because I've written it like that. But I want to explain something. Stick with me very carefully. When we write down the Kc expression for any chemical reaction in equilibrium, and we say you must leave out the water, you must leave out the solid, we are not saying there's no concentration. We are saying because their concentrations are fixed, they are constant, they don't change, there's no need for us to have the H2O on that. So what do we do instead? We remove it. But let me show you where the Kw comes from. So Kc, if I want to get away with, to remove my H2O here, concentration of H2O, I'll multiply both sides by the concentration of H2O. That will be equal to the concentration of hydronium ions times the concentration of the OH minus. I'm doing this just to make you see where this comes from so you can understand it better. Now, if you look at this, you have got Kc, which is some value, and you are multiplying it with a constant, concentration of water, which is constant. And because of that, you come to something very special, Kw, because of this, the equilibrium constant of water. Then that equals the concentration of H3O plus times the concentration of the OH minus. It has ceased to be Kc, it is now Kw. That's where this whole thing comes from. And I believe you understand it now, where that comes from. And it happens to be a constant, which is 1 by 10 to the power minus 14. So equals to that. Okay, we're fine with that. Done, closed.
Okay, last one for now.
Yeah.
His gift in Tabeleng says, what is the difference between ionize and dissociate?
All right. When something ionizes, okay, let's go down and get some space. When something ionizes, it means there were no ions before. For example, if you have the HCl gas, this is a covalent bond. So there are no ions. There are no pluses and minuses. That is the ions we're talking about. So when you put these in water and it forms ions, it forms the H3O plus. Starting with this now. H3O plus the O plus the Cl minus ion. Okay? These ions were not there before. So there was ionization here, formation of ions. Okay? But if you come to bases, for example, sodium hydroxide, this one is already an ion. It is a substance formed by the sodium plus and the OH minus ion. So when we put it in water, it does not ionize, it just dissociates. It just dissociates into that. In fact, you have that at the beginning, then it dissociates to Na plus and OH minus. This Na plus and OH minus are there already, long before you even put it in water. So when you put it in water, the water only helps it to dissociate. So that is dissociation. But ionization means there were no ions before. So they are formed as that process happens. So that is the difference between the two. Can we move on? I know there are others that are talking to conjugate acid-base pairs, and I want to do an example, Abram, before we close this lesson, that would help them understand what those things are. Okay. I think I would have a question here that talks to that. Okay, let me see. I think it's question 4. Let's see. Yes, it will be question 4. Let's look at question 4 quickly. The ionization process for two different acids, so acids ionize, shown here in equation 1 and equation 2, all right? We have that shown. We have got this one here, CH3COOH, okay, plus water, giving us that and that, all right? The second equation is nitric acid reacting with water, giving us that and that, okay? The first question is define the term weak acid. Oh, everybody should be able to tell me what a weak acid is. Weak acid, okay, is a substance or is an acid. Let me just be specific. It is an acid. Okay, it's an acid that you see now. What was the name? Gift or whatever. We see now. I can't say that dissociates because it's not dissociation, but that ionizes almost completely in solution, aqueous solution. Okay, so I can write it like that. That's a weak acid that ionizes slightly, only slightly. Making a mistake now. I'm giving you the one for strong acid. I must give you the one for weak acid. So we're talking weak acid. It's an acid that ionizes only slightly in aqueous solution. So that is a weak acid. Which of the two acids is considered a weak acid? If you go back to this, okay, we know that that is considered a weak acid. HNO3, a strong acid. So ethanoic acid will be the answer for us here. It will be the CH3, COOH. This is the weak acid. Why is it considered a weak acid? Because we have to explain here. It ionizes. It ionizes only slightly in aqueous solution. Okay? In aqueous solution. So there is low percent, it has got low ionization percentage, if you like, low ionization percentage. Okay, low ionization percentage in water or in solution. That's why it is called, or it is seen to be, a weak acid. 4.1.3, write down the conjugate acid-base pairs, all right, for this situation here, or for this chemical reaction here, for reaction 1. So they are specific for equation 1. So if you go back to equation 1, I'm going to rewrite it. CH3, so it's CH3 COOH plus H2O plus H2O, giving us H3O plus CH3COO minus. Okay, so that's what we have. if you look at this, this is the substance that is giving away a proton, which is the H plus ion. H plus ion. So it is giving it to the water molecule. Because it is giving away a proton, it is an acid. But on giving away a proton, what does it become on the other side? When it gives away a proton, it becomes the CH3COO minus ion. So this is the acid, and this one is the base, is the conjugate base of our acid. Let me explain it like that. So the two, this one and that one, are acid base conjugate pairs. Conjugate pairs. All right? And if you look at the other situation, the water molecule. If you look at the other situation, the water molecule, this one, you would see that the water molecule receives a proton, that proton. And on receiving a proton, it means if it receives a proton, according to Lowry Bronsted, that is a base. Any substance that receives a proton is a base. When it receives a proton, it becomes, it was H2O, it receives a proton, it becomes H3O plus. So what does this mean? This means that the two are acid-base conjugate pairs. This one is the acid. This is the conjugate acid. So let me write conj there. Conjugate acid of this base. So the two are acid-base conjugate pairs. Acid-base conjugate pair. These two, the H2O and the H3O plus, are acid-base conjugate pairs. Now, one thing you would have noticed there is that you can't have an acid-base conjugate pair on one side of an equation. An acid-base conjugate pair would be a pair that is consisting of two substances on either side of the chemical equation. So from the left, if you have got an acid, there shall be a conjugate base of that acid on the right. On the left, if you have got a base, there shall be a conjugate acid of that base on the right. That's what it is about. So you can tell from what I have just shown here how you get to that situation.
All right,
now,
TK.
Well, yes.
Just before we end the show, because
Yeah.
I know time is against us,
Yeah.
Mashuri is asking, will I be wrong if I define weak acid as an acid that is partially ionized in solution?
That's what it means. Slight ionization means partial ionization in solution. So that's fine. I'll accept that.
All right, cool. Mashuri,
Yes, I
you'll be
think,
correct.
yeah, time is against us and we have to say bye-bye, and we're still enjoying this. Hopefully you've had a lot to learn from me this afternoon, and from Abraham as well. I know he's a great science student. He's learning so much every day. Thanks, Abraham.
Of course. Thank you, TK. You make the show fun. Guys, thank you so much. Learning doesn't end here. Remember, you can still get in touch with us on our social media platforms, facebook.com/learnextra, or follow us on Twitter. A big thank you to the Department of Basic Education for making sure that we have this show. We love you. Peace.